right now. So without any, I started recording right now. Without any further ado, it's Conrad Aguilar from Pomona College, California. And it is about the Bunce-Deddens Algebras as Quantum-Gromov-Hausdorff-Distance limits of circle algebras. The floor is yours. Take it away.
Yeah, thank you very much. Thank you very much for the invitation. Terribly sorry about the delay. I was confused. Anyway, okay. Yeah, so let's get started with some motivation here. So, our setting is inductive limits, okay, and we'll have this sort of informal definition of inductive limits, so that A be a unital C-star algebra, where for each n and n, an is a unital C-star subalgebra. They're nested, and the closure of the union is our space A. Okay. Now the setting is assumed for each n that each an is a compact quantum metric space in the sense of Riefel, and then we consider the dual Gromov-Hausdorff-Propinquity of La Tremolière, which is a complete metric on the class of certain compact quantum metric spaces. Okay. So the main question is then, how do we then not only show convergence, but first put a quantum metric on the inductive limit? Okay. All right. So how do we first put a quantum metric on the inductive limit from this structure A and Ln, and then from there show convergence, okay, of these spaces? So sort of taking the categorical limit and then translating it to a metric limit, now that we have these tools of these non-commutative analogs to the Gromov-Hausdorff-Distance. Okay, so the idea then is that is highlighted here, that this is a complete metric. So then we want to insist that A and Ln is a Cauchy sequence in there, but unfortunately you need a little bit more than that. Okay, so the idea is that it's a complete metric. So if A and Ln is a Cauchy sequence, it will give us a space, a limit space. Okay, but we'll see that we need some further conditions. We'll see a counterexample that if we just assume A and Ln is Cauchy, then the limit space will not be actually isomorphic. The F space here that I state here may not be isomorphic to the full inductive limit. Okay, so we will have to have extra conditions. Okay, so the consequences of being able to do this is we'll be able to extend our work with La Tremolière that we had on unital AF algebras with faithful tracial state. So to all unital AF algebras, and the idea is that, well, any finite dimensional C-star algebra will have a faithful tracial state. So then maybe we can capitalize on that and then extend that to an inductive, use the methods we have here to extend that to a quantum metric on the inductive limit. Okay, and then we'll see this, how to extend it to Bunce-Deddens algebras, which are not AF. So there'll be some issues that we'll run into, but we'll get to those when we get there. Okay, now let's do some backgrounds on compact quantum metric spaces. So that XD be a compact metric space, the idea then, how do you make a non-commutative analog of a quantum metric space? You look into the classical case first, right? And we can already capture the topological structure of any compact Hausdorff space, okay, within the state space. So this map here is a homeomorphism onto this image with where delta sub x is the point mass or the evaluation map. And if we can somehow boost this up to an isometry, then we have captured the metric structure, okay, in the C-star algebraic structure of the state space. But of course, to first do this, you need to talk about a metric on the state space. Of course, the state space is, because X is compact metric, the state space is metrizable, of course, but it's metrizable in the weak star topology, but we want a little more than that. We want more detail to be able to capture the structure of X. Okay, so recall that the Lipschitz seminorm is defined to be this. Okay, so it just takes the Lipschitz constant. So the method to do this is to consider the Lipschitz constant, okay, which takes the maximum slope. Of course, it's informal because we don't know what the metric is on X, but that's the idea. And then with this, you can define the Monch-Kontorovich metric on the state space, defined for any two states by phi and psi in the following way. So that the idea, the important part is we take Lipschitz functions less than or equal to 1. I mean, the idea is that that'll help the point masses recover what we'll see in the next slide, at least in one direction, right? This is just delta sub x of f, and this other is delta sub x of y. So that's one way, and then you can actually obtain, right? So the idea is we want to be able to capture the metric on X here. So that's in fact what happens. Attributed to Kantorovich here. And then we list some properties here that are obtained. For example, the seminorm here, because the idea is we want to make the non-commutative analog of it. So we want to see some seminorms for which this does, in the non-commutative sense. So we want to capture some properties that can be abstracted. So for example, some of these statements here, like the elements for which is finite is dense, that maybe can be, just stated. Maybe we have some sort of semi-norm on some non-commutative space for which we get such a property, right? Same thing here. The elements for which it vanishes are only the scalar multiples identity. Of course, in the classical case, those are the constant functions, but you can think of this as just scalar multiples identity in the non-commutative case. Anyway, so we do have this, what we just said, we do obtain a metric on the states. Sorry, there's some noise. I'll try to talk loudly. So we do obtain an isometry from X into the state space of C of X, okay, via this map now. This Bunce-Deddens metric does it, and I already described a little bit of the, why it does it. Take the point masses here, and you actually get f of X minus f of Y. Okay, and also you want to be able to capture the topological structures, so you do get that. You metrize the weak star topology on the state space. Okay, so that's nice. And also some other properties we want to look into, for example, is the multiplicative structure. This will matter for first half of the talk, but later on we'll see that we don't get such nice properties for some of our examples later on.
Okay. Which year was this theorem proven? When was it proven?
I believe it might have been. I should know. I think it might have been the 60s.
Okay.
If I'm.
Yeah, just what the rough estimates. Yeah. Mm-hmm.
Yeah.
40s to 50s, really. I mean, 1940s
okay.
when Kantorovich really did it. The form that we're talking about is 58, and the Wasserstein thing is like 70, very late 60s, 70s. But that Kantorovich really came up with it technically in the 40s.
Okay. Thank you.
Mm-hmm. Okay. So then, so motivated by the work of Kohn, Riefel introduced the notion of a compact quantum. So Kohn already had a metric induced by the spectral triple using the norms of the bounded commutators, with the Dirac operator. But so Kohn's already introduced that, and then Riefel introduced a pair is a unital C-star algebra and a lower semi-continuous semi-norm. Of course, this definition has been tweaked throughout the years, but this is the definition we'll take in this talk. So we define it on all the subadjoint elements, but we allow it to take value infinity, so it should be an extended. We should put the adjective extended semi-norm, such that on the domain, so there's a domain that's dense, for which it is finite, for which it is a legitimate semi-norm, is a compact quantum metric space if the elements for which it vanishes on are the scalar multiples identity. Of course, we're talking about subadjoint elements now, so we only consider real value scalar multiples, and the associated Bunce-Deddens metric on the state space defined for all states by that metrizes the weak star topologies. So of course, these conditions before it aren't enough to do that, so we impose that we metrize the weak star topology. So we call L a lip norm when this does happen. And then we see on the previous slide, these are things that, C of X itself is a compact quantum metric space. We'll have other examples here later on in this talk, but for now we'll note that. And a Bunce-Deddens metric we'll call the compact quantum metric, or just the quantum metric. And we also note that you can actually recover, in this setting, you can recover because now you have that continuous function of the state space is a the state space has a metric, so the continuous function of the state space is now a compact quantum metric space itself. So you can actually recover. What's nice is you can recover the lip norm here, L, this abstract lip norm on A, by a concrete lip norm, right? A concrete lip norm coming from the Bunce-Deddens metric on the state space. Okay, for all elements in the domain. And A hat is just the evaluation map is defined for all that. So yeah, so that's nice to sort of have that tie back to, of course, we remark whenever we say this that it may be the case that you do have a quantum metric, a Lipschitz norm on C of X such that L is not recovered by the original Lipschitz constant. So, just so that there's notice, we're not just taking the pure states here in the denominator. We have all the states here. So I don't think this is a flaw or anything. I just like to note that there's this technical detail. Okay. There were also nice equivalences for compact quantum metric space. For example, one thing that we use often is the following, that you have still the conditions of density of the domain, you have vanishing on the scalars, but you can replace the condition that you metrize the Weak-Star topology with some statement like this. There exists a state such that this set is compact for the norm on A. There's other ones too. You can look at the quotient by the scalars and say that's compact. But these end up being much more useful, much easier to prove metrization of Weak-Star topology or statements like these, which are nice to give a more concrete idea of what's happening. Okay, so I mentioned this Leibniz inequality when I was discussing the classical case. It turns out then the examples where we do have some sort of Leibniz condition, it'll be of the form of a CD quasi-Leibniz condition. So as we saw, we look at the self-adjoint elements. There are various reasons for this. One, reaching back to the classical case, is that you can extend Lipschitz function, real value Lipschitz functions on a subset to a bigger set and still preserve the Lipschitz constant. If you consider complex value Lipschitz functions, that's not always the case. So, so that actually appears in some work related to quantum metric space. So that's, it is important to look at the self-adjoints if you can. Anyway, so because we're looking at the self-adjoint elements, we can't just take their products, right? But we still want to capture some multiplicative structures. So here we have a Jordan product and a Lie product. And here, in the classical case, we had C equals 1 and D equals 0, but we're allowing for other scalars here. In this talk, we'll see C equals 2 and D equals 0. So D will be 0 still, but we will have C equals 2 in some of our examples later on. Okay, so so there are many examples. Non-commutative tori were the first ones we will get introduced, and then curve non-commutative tori, various classes of group C-star algebras, including hyperbolic group C-star algebras, AF algebras through Antonis Christensen, my work with Laux Romier, and some other work I did later on. Some work we presented this talk, non-commutative solenoids of Laux Romier and Packer, of course, and also some more self-promotion, the standard quantum polar sphere. There's of course a typo there, unfortunate typo. But this was the quantum metric specifically. So I mentioned this detail here is because the standard quantum polar sphere is the unitization of the compact, which is in AF algebra, and here we present quantum metrics on all AF algebras. But the point is that we didn't just put a quantum metric on it as an AF algebra. We actually used a quantum metric given by the Kohn metric associated to the Dabrowski-Sitar special triple. So we were actually capturing some of the non-commutative, the standard non-commutative geometry there with our quantum metric. So I'd like to point that out because that was the fun part of that. Okay. The next we have. So I introduced these spaces to you that you may not be familiar with. So then it's nice to understand what does it mean for them? What do we take them as to be the same? Okay. So much like compact metric space or just metric spaces, you think of them as the same in the sense of there's an isometry, right? So the idea is that we have a C-star algebraic structure, right? And we have a metric structure, right? So one may think, okay, we want some sort of isomorphism at the C-star algebra level and some sort of metric at the states, right? But the issue is that you want to be a little more careful with those conditions. You actually want a star isomorphism at the C-star algebra level, but you want that star isomorphism to induce the isometry between the states. You don't just want two separate things. You don't just want isomorphism at the C-star algebra and a separate isometry you want it to be induced by the dual map. In particular, one reason you want that is you get the following as well. You get that these two spaces are quantum isometric if and only if there exists an isomorphism that intertwines the Lipp norm. So that's another reason why you want the star isomorphism to be the map that gives you the isometry between the states. Okay, so now that we have these spaces, we know what we want them to be the same. So in particular, we want to define a quantum. We want to find a distance between them, like non-commutative Gromov-Hausdorff distance between them. So right now we have a notion of now we have a goal for what we want distance 0 to be. So this is another reason why we introduce quantum isometry. We define it here because now we have a goal for, okay, what should distance 0 be, right? So let's see how that can be obtained. So we look first at the classical case, the Gromov-Hausdorff distance. The idea is that you can take any two compact metric spaces, you can embed them into a third metric space, okay? Isometrically, you can always do that. You can always find a third space to do that. And in there, you can take Hausdorff distances of those, okay? So then the idea then is to say, okay, we can do that many times, take the infimum. Turns out this isn't too much to take the infimum. In fact, it's exactly what you want in the sense that the Gromov-Hausdorff distance is 0 if and only if there exists a surjective isometry, okay, from X to Y. So you do get the distance 0. Of course, you can never hope that the sets equal. They could be in just different spaces entirely. So this is the best you could hope for, and it's what you want. Okay, and the Gromov-Hausdorff distance is in fact the complete metric on the class of compact metric spaces. And again, that's a big theme in this talk, is to get distances that are complete so we can actually produce new Lipp norms. Okay, so now how do we make a non-commutative version of this? Well, the idea is that the standard thing to do is to use duality, right? So the idea then is that these maps, your embeddings, actually induce surjections, okay? And it flips the arrows, right? We have surjections from C of Z now onto C of X and from C of Z onto C of Y. So it turns out for quantum metric spaces, we want structures like this capturing our distances, okay? We don't want embeddings, we want surjections, okay? Okay, so then we have a notion of a tunnel, and the idea is just to copy that, but make sure we still capture metric structure in some way by doing that. So we let those be two CD quasi-Leibniz compact quantum metric spaces, a CD tunnel, or just a tunnel when the context is clear. Is a third, just like C of Z is a third space, okay, with its own Lipp norm, and two surjective homomorphisms, star homomorphisms from E onto E1 and E onto E2, for which the Lipp norm, if you take the quotient semi-norm with respect to that Lipp norm, you capture back the each of the Lipp norms you started with. So here we have L1 is captured by LE, and L2 is also captured by LE via the surjections. Okay, so this is a picture here. I don't think I do, no. So, well, I guess I mentioned on the next slide, but the idea now is that what this does actually do is that now when you actually switch these with the state spaces, you actually get isometric embeddings back into the state spaces. So you still get the picture from the Gromov-Hausdorff distance picture. Is just you have to go to the level of states now. So you start at the level of the algebra, but you can still capture the isometric embeddings and the arrows will switch if you consider the states and the associated quantum metrics or the Bunce-Deddens metrics. So you still get the classical picture appearing here. And with that, because we have isometric embeddings, and that's via the dual maps. So pi star A, I have a frac A here, but it should be pi sub A. This is an isometric embedding in the state space, as I just mentioned, and so is pi star B, okay? And then we compare them with the entire state spaces, state space of E, okay? And this is the extent. So this is like how in the Gromov-Hausdorff distance, we have the Hausdorff distance between the Hausdorff distance between the images of the spaces. So this is a little different though, right? We didn't just take the Hausdorff distance between pi star of A, of S of A, and pi star B of S of B, okay? This is Latremer split it up, and the idea is to get the triangle inequality. Well, part of the idea is to get the triangle inequality. So there's a lot of subtlety here going on, but there is a reason to do that. It's not just to complicate things. Okay, but that's the value we associate to a tunnel. Okay, and then we take the infimum over all those, and so in a similar way to how we did before, Gromov-Hausdorff distance wise. Okay, and this does in fact form a complete metric up to quantum isometry. So distance 0 gives you a star isomorphism that intertwines the lip norm. So we get everything with the algebraic structure. We get the algebraic structure, the entire CC algebraic structure, and on top of that, the quantum metric structure as well, the Marshall-Torgovich metric. And it is a non-analog to the Gromov-Hausdorff distance, in part because you can actually, if you look back at the classical case, the quantum distance between the dual propinquity distance between C of X and C of Y is actually bounded above by the Gromov-Hausdorff distance. So this gives you, if you think of this as if you think of a map from compact metric spaces to compact quantum metric spaces, sending X to C of X, this gives you a map that's Lipschitz in that direction. Okay, so it gives you a continuous map, right? The issue is that there's no inequality the other way, but you can still show that and you can show this map is injective with respect to the equivalence relations of isometry and quantum isometry. So we actually get an inverse map. You can show that that's continuous. Okay, so you actually capture the entire Gromov-Hausdorff distance topology within the dual propinquity topology. And this is building, of course, this distance is building, of course, on the work of Riefel. And why am I not? I'm actually going to define Riefel's quantum Gromov-Hausdorff distance later. So I'm sort of saving that for later. But this is very much motivated by much work, Riefel's quantum distance, Kerr and Lee, David Kerr, Hanfing Lee's distance, and many others to get to this point. But yeah, we will actually define and use Riefel's quantum Gromov-Hausdorff distance later as well.
Sorry, Konrad, just a silly question, if I may.
Yeah, of course.
Why is this propinquity less or equal to the Gromov-Hausdorff? Why is it not equal?
So there is actually an example given by Hanfing Lee, and Riefel puts it in his appendix on the Gromov-Hausdorff distance for quantum metric spaces paper. And I guess so that there is a counterexample out there that does an example that gives you strict inequality. But I would say philosophically wise that we're measuring distances between the entire state spaces, not just the pure states. So we're sort of, filling up kind of too much in a way. So the estimates are tighter since we have bigger spaces.
It's easier to be closer together because
because you're bigger. Yes, very
okay.
Yeah. Thank you for saying it that way. Yeah,
that's exactly. Thanks.
Yeah. Okay, so there are many examples of convergence in this. So the matrix algebras converge to the sphere, which is one of Riefel's first convergence results. And there's convergence of fuzzy tori to quantum tori, including the non-commutative torus as well. So you do get a sort of matrices converging to the torus kind of picture here. And you get convergence because of fuzzy tori or matrix algebras. There's subalgebras of matrices. And convergence of quantum tori themselves. Not just the finite dimensional approach, but you use the finite dimensional approximation of fuzzy tori to actually also get convergence of quantum tori. Convergence of UHF algebras and F-Roshan algebras. We'll mention more detail about that later. And convergence of quantum tori to the non-commutative solenoids and many other examples that we'll get to. We'll get to in this talk, and also the Bunce-Deddens algebras and things like this. So so now what's next is that I'd like to go over how one obtains now estimates. What is one route one obtains actual estimates for the dual propinquity. And one thing that we use often is the Oshadova bridge. And this is actually that's a Latremer bridge. There were Riefel bridges too, so to distinguish between those two. So here we have The idea is that sort of directly comparing. So the tunnels, they took surjections, right? Here you can actually, there's a way to estimate by taking injections, okay? So this is using the notion of a bridge. So it's a third space that contains isometrically A and B via unital star monomorphisms, unital star injective homomorphisms. And then we have a pivot element here that sort of just tweak our estimates as we please. And just an example of a pivot element is this identity element, which is what we use mostly. Just take the identity element in D, and in fact you get the entire state space if you use the identity element as your pivot. But to be a pivot, this has to be non-empty, but if the pivot is 1, it's of course non-empty because you get the entire state space. Okay. Okay, so then to take estimates with this, we introduce the bridge semi-norm. We define, well, it's defined by electrometer as well. So this is how your pivot will be tweaking estimates in the space D. Right? You actually commute, we'll take the commutator, I guess, with it. And then you associate some quantities to it. So before the tunnel, we had this nice single quantity extent, but the idea of a bridge is that you can sort of be much more refined in your estimates. You can take many more. You can sort of split up your estimates into different parts, some different moving parts, so you can capture some other structure. So the idea is to use the bridge to calculate distances at the level of the C star algebras, and also calculate distances, separately calculate distances at the level of states. So the reach calculates distances. So you're just taking the Hausdorff distance of the lip balls as they are embedded in the bigger space D. So here's your bridge semi-norm here. That you're using that. So this is distances between the lip balls essentially, and then you also want distance between the states associated to this, right? Okay, and again, this is a nice picture because that's how you're producing quantum isometries, right? You have star isomorphism at the level of the algebra, you have isometries at the level of states. So it's nice to know that there's a way to actually provide estimates with that same philosophy. You're doing estimates at the level of the algebra and estimates at the level of the states. And then you just combine those two by taking the max, okay? However, we want to be able to use these estimates, right? We have dual propinquities that's defined using tunnels, okay? So we want to be able to use these estimates to define a tunnel to be able to apply that to the dual propinquity. So this is a way to do that. If you have a bridge with a specific, you take any value bigger than the length, then you can define a lip norm on the direct sum. You just take the max of each coordinate with respect to the lip norms you have on those spaces, and then you take the bridge semi-norm, okay? And this actually gives you a tunnel where its extent is at most 2 lambda, this value that's bigger than the length of the bridge. And we're using the canonical surjections. I guess I use pi A, pi B later. And then you get a legitimate estimate in dual propinquity using the bridge. And that's mainly our approach on estimates in dual propinquity.
So you build tunnels out of bridges?
Yes, yeah, that's a little bit. That's a strange.
But more seriously, would you care to explain, at least very briefly, what is such a bridge in the classical setting of compact metric spaces? Because then what, you use quotient maps, right?
Yeah. So I'm not sure if there's an actual. I feel like a bridge is. Yeah, I mean, yeah, the tunnel comes from, as you saw before, it's just the dual picture, right?
That's clear.
Yeah. But bridge, I'm not sure if there's a real classical picture for that. I mean, directly you have isometries, right, from the spaces, but as far as I don't know, maybe Frederick knows more.
I claim innocence. No, the bridges, in a sense, they're fundamentally non-commutative, right? Because you're commuting with a pivot thing. So there is no, this is not something people would look at naturally in the geometric sense, because it's commutation with an element, So the short answer would be no. Now, what's interesting is the way you do prove that there's a relation between Gromov-Hausdorff and the propinquity does involve, in fact, a bridge. So it's constructed by, embedding two spaces into a third one, and then looking sort of like at the pair of points from one from each space, which are closed in that third one, and that's how you make a bridge. So there is a picture there, but I would say that overall, especially when the pivot is non-trivial, it's a very much non-commutative idea.
Okay, great. Yeah. Thank you. Okay, so then, so next we have, we'll use this to give some examples of now inductive limits as metric limits. So, and then, move into our goal of, taking quantum metrics on terms in the inductive sequence and putting quantum metrics on the inductive limit from that. So not knowing there's an inductive limit on the limit space to begin with. But that's not how we first did things. So we first were able to, when you have an AF algebra with the faithful tracial state, we were first able to put a quantum metric on the inductive limit to begin with. And that gave us quantum metrics on the inductive sequence. And this is sort of backwards, but we were able to do it. So we went with it. And it was nice. It gave us a nice picture. So the idea is that for the AF algebra case, if you think in general, you want to be able to build a quantum metric that does, and if all you know, if you have an AF algebra, that's all the structure you just know there's this finite dimensional space building up to it. So the motivation to build a quantum metric on this is just to show that the AN spaces do converge, okay, to the inductive limit. So the idea is you want to be able to provide nice estimates from A to AN, and what a faithful tracial state does, it gives us a very nice way to do that. It gives us unique trace preserving conditional expectations. Okay, so to provide us estimates between A and AN. Okay, and then we just build our lip norm to capture those estimates. Okay, meaning we take a sequence converging to 0 and a positive sequence converging to 0 at infinity. And if for all A and A we said this, then yeah, we're actually controlling the distances here, and the sequence is going to 0. And the idea is that, remember, we are comparing distances of lip balls, right? Lip balls of size 1. Okay, so if this has lip norm less than or equal to 1, then the idea is that you are actually imposing, and since beta is going to 0, you just multiply both sides by beta. You actually are getting that the En of A are converging to A. Okay, so this is essentially like the motivation for why this is built this way, is to capture that. So as this ends up giving you automatically a quantum metric on the inductive limit. And also in this case, it's not always the case that subalgebras do this, but in this case, we actually get that. It restricts the quantum metrics on each AN, and you get an explicit estimate. So this is, I like to state this here. This isn't just you don't just get some magical convergence result. You actually get a very concrete convergence result. And of course, one thing you can take beta to be is just the reciprocal of the dimensions, right? So you get a very nice, so any sequence converging to 0, but in particular, you can compare it with dimensions, the reciprocal of the dimensions, which we actually use in our work. So yeah, so this was a case where we were able to get our results, but then from here, the natural question arose is, can we do this without a quantum metric on A to begin with, right? And also, can we extend this outside the faithful tracial state case? Okay, but first, we'll cover an example. We'll just show an application of this. So for example, we let A of theta denote the Efrosham algebra associated to theta. So Pinzer will let us utilize these to classify the irrational rotation algebras with respect to the rational parameters. Of course, later on, Elliott and Evans, in their paper, George Elliott and David Evans, proved that put the rational rotation algebras into the class in the Elliott classification program. So that also captures this too. Okay, but before that was Pinzer-Voculescu in a different route just said, okay, do we have that A theta is isomorphic to A theta prime with respect to the rational parameters, if the rational parameters are equal, if and only if the rational parameters are equal. And so they were able to do that. And the idea is they did it by embedding them into AF algebras, okay, associated to irrational parameters. So we let this denote so then the idea is, okay, if we have irrational rotation algebras already converging due to the work of Latremouille, do we also have the these AF algebras converging as well with respect to the rational parameter. So conveniently, these have unique faithful tracial states, so that's nice. And then here we do take the beta sequence to be reciprocal to the dimensions, and we do in fact get that continuity. We get if the rational numbers converge, then the associated F-Shan algebras converge as well. So yeah, so this so that structure was enough to get us such a result here. So now, what about without faithful? What about having, maybe you don't have a faithful tracial state, for example, the unitization of the compact operators. Can we still get this, the inductive sequence converted to the inductive limit? Okay, but the issue is that we can't use this trick anymore of having a faithful tracial state on the whole space. Okay. The idea is, though, that each finite dimensional C algebra has a faithful tracial state. So can we somehow capitalize on just looking at the terms in the inductive sequence? And you know, and this is sort of the theme of inductive limits, right? The idea is that you should be able to get the structure of the limit. The point is that you get the structure of the limit from the structure of the sequence. Okay. So we're trying to just, you know, we should be able to do that in some way with quantum metric structure. So there's that just philosophical idea of just, you know, we should be able to do this in some quantum metric way. So then, as I mentioned before in the beginning, the idea is to use the fact that the dual propinquity is complete. So there is a metric way to build a, we can actually build a something on a limit. Okay, it's a metric limit, right? But maybe we can combine that with the inductive sequence structure. Okay, but unfortunately, it's not enough to assume that our inductive sequence is Cauchy. Okay, we need further conditions. Okay, so the example I present here is, so consider the Car algebra, which is an inductive sequence. So it's a canonical anti-commutation relation algebra. Is an inductive sequence of, so it is AF. It's an inductive sequence of simple matrix algebras, actually, for all n and n. And you can't, so I'm not defining them explicitly here, but you can put lip norms on each an such that the following happens. You actually don't get that they're contractive, okay, with respect to just the inclusion map, right? But you still get that they're Cauchy. So the idea is that when you are building, at least in analysis, if you're trying to build some sort of inductive limit structure, the idea is you want sort of contractivity of your structures. Okay, so the point here I'm making in this example is that's what we want, because even though this is Cauchy, this example doesn't have this. So morally, this is why the following happens. So again, it's Cauchy, so in dual propinquity, so dual propinquity is complete. So there is a limit space, and you can show that in fact it does converge. Okay, well, I mean, obviously, you don't have to show it's complete. So it does converge to this space. However, you do get that you can show that the inductive limit you get from propinquity, not the inductive limit, the metric limit you get from propinquity is actually isomorphic to this complex numbers. Okay, which is clearly not the Car algebra in infinite dimensional space. Okay, so this is showing that Cauchy is not enough. And the idea is that you want Cauchy and something like, you want this inequality to happen. This you want to have the contractivity of the lip norms as well. But in fact, you want a little more too. So let's finally define exactly what you need. So what on top of Cauchy do you want? So it is here, it's like I call this propinquity of proximal. But here we have property one. So we have an inductive limit for which each term of the sequence is a compact quantum metric space. So again, we're not assuming the inductive limit itself has a quantum metric on it. Yeah, we're not assuming that it has a quantum metric on it to begin with. We do assume each term of the sequence does, and we have contractivity of the lip norms. And we impose Cauchy in the following way in property two. We assume that the sort of obvious choice for a bridge, which is just the, these are contained in each other. So just take the embeddings. So I'd have a little picture here. Our embeddings of an into an an plus 1 is just inclusion, and our embedding of an plus 1 into an plus 1 is just identity. Okay, and in that case, we get very nice estimates. The bridge semi-norm just becomes the norm difference of our elements. Okay, so property two, we don't explicitly say Cauchy, but we do get in fact that property 2 gives us, along with property 1, we do get that if we compare consecutive terms, we get that it's less than or equal to 4 times beta of n. And notice here, we're not just assuming beta is a convergent sequence. Okay, we assume that it's summable. Okay, and this is why, because we can only compare consecutive terms. So if we want to get a Cauchy sequence from consecutive terms, if you have a summable sequence, then you do get Cauchy, right? This is standard analysis exercise. Okay, so we don't explicitly say in this definition, okay, assume contractivity and then Cauchy. We want a more, we want something to imply Cauchy, something a little more explicit that is utilizing the inductive limit structure, right? The bridges are coming from the inductive sequence structure. Okay. So we do get the result. We do get that A is inductive limit of C-star algebras. Well, if we assume that, then and the previous conditions, we do get that the union of the domains actually are contained. We do get a lip norm on the whole space, okay, and the union of the domains, so in a nice way, are contained in the domain of the new lip norm we get on A. And we do get convergence, and also a concrete estimate with respect to the tails of the series. So again, this is part of the goal too, is that we actually get concrete estimates for a limit. So and thus we automatically get convergence. So the idea is to utilize concrete because that's what worked before in the AF algebra. The AF algebra with faithful traceable state case, we did get the concrete estimates did help us out with that. Okay, so then I'm going to go through the idea of the proof a little bit. So the proof uses explicit construction of the limit of Cauchy sequence and dual propinquity. So any completeness argument that exists for any, any metric space, it builds a limit in the argument, right, in some way. So we actually use the construction of the limit in the dual propinquity paper of La Tremouillère. So let's go through, how do we build the lip norm on the inductive limit? Okay, so the process is the following. So it's a little technical, but so the idea is that, so to assume you have this inductive limit picture and each AN is a quantum metric space. Okay, so first define the product of the consecutive terms. So these are our tunnels essentially. So it looks a little weird why we're, why not just take the product of AN itself? The idea is we want to be able to use the tunnels, which are these direct sums. But K0 says already immediately the space K0 that again these are all just terms taken from the completeness argument in La Tremouillère's paper. So again, we're just plugging in our structure into the completeness argument. So K0 we have, I probably shouldn't use K0. That's K3. But this is not the same notation. So here we have, this is essentially saying it is just products of AN, because all we're saying is they take pairs, okay, and then for any consecutive pair, the middle terms agree. So this set itself is already saying, like, trying to forget that there was, we're taking products of pairs, we're just taking the products of AN. And then the next thing is to define a lip norm on that. This is essentially, again, just using these tunnels pictured before. This, how to build tunnels from bridges, right? We took the lip norms, max of lip norms at each stage, and then we sort of did the bridge semi-norm. So that's all this is doing here. And this is, again, this is just what's happened when you plug things into the completeness argument. You get the natural things that we started with before. And then we define the set of elements for which, so essentially the domain of this semi-norm here, right? So we're getting at building our lip norm, but we actually want to build a C-star algebra as well at some point. Okay, so then we take real and imaginary parts of D. Okay, so we're sort of trying to build a complex structure. So here we're starting with the self-adjoint structure. Okay, so this is what G0 does. Then we take its closure. Okay. And then we sort of, we are sort of doing a kind of an inductive sequence thing, right? This is where the inductive sequence picture is sort of appearing. And again, this is just naturally appearing from plugging things into the completeness argument of La Tremouillère. And then you take the quotient and you do get a unital C-star algebra. So this is our limit space, right? Just the limit C-star algebra, okay? And you define a semi-norm on it by taking the infimum of S sub 0 D for all elements in here that are images under the quotient map. Okay, and this actually gives you a lip norm on F. So FLF is the limit given you by the completeness argument. Okay, but because of the nice setting we're in, because we're assuming that the lip norms are contracted, we're assuming that we have these estimates with respect to the bridges, you are able to use the universal property of inductive limits to build an isomorphism from A to F, such that, and then you define L sub A, right? Because remember, A doesn't have a quantum metric to begin with, so this should be a L sub A with the colon equals. You define L sub A to just be the composition with respect there, so with respect to the isomorphism and the lip norm that's already on F. And then ALA is a quasi-lemmas compact quantum metric space. Okay, because LF was, and if you compose with a star isomorphism, you get everything for free. So yeah, so it's using the completeness argument, and it's using, so it uses, I think, natural things. It uses the completeness argument. It also uses the universal property of inductive limits, right? You use these if you have embeddings at each level of the AN. So the idea is you can capture the ANs essentially sitting in here, and the idea is you embed these in an appropriate way, and you make the diagram commute with the embeddings for the AF for the inductive limit, and then it automatically boosts you up to an isomorphism at the level of the whole spaces, and then you just check some details, and you check that it's injective still, you check that it's onto surjective and all that.
So Conrad, again, a trivial question, if I may. How do you see the unit in this unit of sister algebra F? This is elaborate construction trying to trace it down. So you say it's a quotient of E0 by J0.
Yes,
but
yeah.
I look at E0, this is a norm completion of G0. I look at the G0, that's something which is built out of sequences, right?
Yes.
And
so it is just the identity element that's just in each coordinate.
Okay. So here, yes. Oh, okay.
Yeah. So we are just taking the identity elements just being repeated in each coordinate. Yeah.
The product of pairs. Okay. Okay.
Yes. Yeah. The product. Yeah. Yeah. It's part of the pairs. Yeah. Thank you. Yeah.
Okay.
Okay. So for the AF case, you just you again use the fat. So applying this to the AF case without faithful tracial state, with or without faithful tracial state, each AN has a faithful tracial state. So you just do this construction we had. It's a little uglier, but we just do this construction we had before, just at each AN. And this builds lip norms that satisfy the conditions that we need for the theorem. So I mean, this is just technical stuff, but I mean, all we're doing is just doing what we did before at the whole AF algebra, just at the finite dimensional bits. And then we get, and then we get what we want. We get a lip norm on the whole AF algebra, and then we still get convergence. So we don't get, just to see, we get the tail of a series, but it's still concrete enough that it does, have this a similar philosophy, right? We are able to compare concretely, in a way, our estimates, which was one of the goals. And here we have this isn't that important for the context of this talk, but I mean, we do have a comparison with the lip norms. This lip norm we have, this magical lip norm we get from the completeness argument, and the lip norms that we originally had on each AN. So we do finally have the unitization of the compact operators in this picture, where we have the convergence of the ANs converging to the full space. In with a concrete estimate, which is nice. Okay, so that was how you did it in the without faithful tracial state case, with or without faithful. What happens if you look at the faithful tracial state case now and you apply the same construction, right? In the faithful tracial state case, you still have faithful tracial states at each level. So what's nice is, in fact, if you apply this new construction, this completeness argument, to the faithful tracial state case that we had before, which was this lip norm, we actually get that the spaces are quantumized similar. The two different constructions of the lip norm on the whole space. So again, the faithful tracial state case gave us for free a lip norm on the inductive limit. The other construction built a lip norm on the inductive limit from completeness. We actually get a quantum isometry between those two compact quantum metric spaces. So in this sense, it's a generalization. Like we were able to achieve a generalization in the non-faithful tracial state case. So that's what this theorem is saying. Okay. All right. So next, we have, now let's go to a non-AF case. Okay. Let's go to the Bunce-Deddens Algebras. Okay. So given a sequence of positive integers, the Bunce-Deddens algebra. So I'm not going to define them completely. I'm going to define pieces of them. It's quite a long-winded construction. But the idea is that these are inductive limits. So they're built of positive integers that. So they're built in similar. They're built very differently, but there's things that are similar with the UHF algebras. Okay. So for example, you build them by a sequence that of non-negative integers where the previous term divides the next term. Okay. All right. But in this case, each of the spaces here, the n spaces are actually isomorphic, not to just the matrices, they're isomorphic to continuous functions, matrix valued continuous functions on the circle, on the one-dimensional torus. Okay. And again, I'll go through more detail of the construction in a moment. But for now, we'll note this B of the sequence, the Bunce-Deddens algebra, can be actually classified with Kn in the same way as UHF algebra. So you get a supernatural number with respect to this, something called a supernatural number with respect to this sequence. And then you can actually show then that if those supernatural numbers are equal, then the supernatural numbers are equal if and only if the Bunce-Deddens algebras are isomorphic. So, which was what happened with the yeah. Okay. So these can also be constructed as inductive limits of C-star algebras of periodic weighted shape where Kn is the period. So there's a few ways to look at this. They're fascinating C-star algebras. But here again, our goal is to show that we can have quantum metrics on here. Can we build a quantum metric on the inductive limit then from that, and then move on from there? Okay, so then the idea is given. Okay, so to show how this is constructed a little bit, we're not going to just take this general thing. So the idea is that we only need to have that the previous term divides the next term, right? Of the scalar with the positive integer here. Okay, so the example we'll look into is just mn and then mn. Oh, yeah, this is a tongue twister. I shouldn't have used this. Mn and mn. Okay, so this n divides that, right? We're just having that term there. So let's see how we can embed that into that space. Okay, and that's essentially how the Bunce-Deddens algebras are built in general. Okay. So you take this thing called the m times around embedding. So the idea is that you take a function on the circle. Okay, so first we won't look at a function on a matrix-fied function on the circle. The idea is we'll take a function on the circle and then we'll just tensor it. And then we'll get not just a matrix n matrix-valued function, we're going to mn matrix-valued function. Okay, so the idea is if you take some unitaries, okay, so you define a map now from a m matrix valued map, okay, in the following way. You take t, an element of the circle, and then you take the diagonals with f of t over m. Okay, so you're sort of shifting these values as you move, and then you're conjugating with the unitary matrix given by these elements here, okay, related to the roots of unity. Okay, so there's not much. I mean, the point about this is that there's a lot going on here. So this is m matrix valued functions. So then you tensor this with the n by n identity matrix. This whole construction, you tensor it by the n by n, the n by n matrix element, identity element, and then you get an embedding from mn into mmn. Okay. From this construction. Okay. Moreover, the point for us is that we do get a conditional citation from the bigger space onto the image of this map. Okay, because remember the way we did estimates, the way we built our lip norms in the AF algebra case is that we need a conditional citation. So the same thing here, we want to follow that same philosophy.
And sorry, what do we know about these unitary matrices, UMT? Just arbitrary? Oh, sorry, this is this ZMJK. Okay.
Yeah, so the coordinates are built from these like roots of unity kind of pieces. Not quite roots, but yeah.
Mm-hmm. Yeah, I'm so sorry. I just
No, that's fine. Yeah, no, that's a lot of
very concrete. Yes.
Okay. Yeah, a lot of stuff on the slide. Yeah.
Exactly.
Okay. Yeah. So moreover, okay. So we do get so the idea is the embedding helps us compare things forward, but we want to eventually compare things backwards, right? So this is where the conditional expectation comes into play. Okay. So, but in the AF case, we were in the fortunate situation that we didn't really have to worry about quantum metrics on each term of the inductive sequence. That was sort of, it's very easy to put quantum metrics on the finite dimensional spaces. And in fact, the ones we built automatically, just for free, gave us quantum metrics on the finite dimensional spaces. Here, though, we have to try a little more. We have to put quantum metrics on the circle algebras. Okay. So the idea is that it's not too complicated. I mean, you have a Lipschitz constant, right? So that's a natural place you go to first. However, the kernel of this is too big, right? If this is 0, then you're right. You need your kernel, right? This is part of the definition of a quantum metric space, right? Your kernel then needs to be just scalar values, okay? So that's not the case. The kernel here is matrix value, right? The kernel here is so these become constant functions still, but they're constant matrix value functions if this value is 0. So there are a few ways to fix this. Bice and I introduced a few ways in this paper, Tristan Bice and I. But in particular, the one way we'll focus on in this talk is the following. In fact, with respect to the circle algebra, you can take the max of the Lip norm of the Lipschitz constant, okay, and then you just you take the norm of A minus any state. Actually, would work. But here, with respect to the Bunce-Deddens algebra structure, that is not entirely clear, but that I did not make entirely clear. But the Bunce-Deddens algebra structure, we do want this trace to be the integration of the circle of the trace of our matrix A. Okay, because again, they're matrix values. Take the trace, take the integral of that over the circle, and then 1 over n, just to normalize it. So the idea is that there is a faithful tracial state on the Bunce-Deddens algebras that comes from this. So that's where this is coming from. That comes from this, just the integral with respect to the Lebesgue measure. I mean, now you're just using Riemann integration because you have continuous functions, but still. So again, I'll mention that too. The Bunce-Deddens algebra has a faithful tracial state on the whole thing, but we can't. Our spaces aren't finite dimensional, so we don't get the same structure. So the conditional expectations actually we got for this work here at between each space that we had on the previous slide, those are actually built explicitly. We actually just had to construct the conditional expectations. We didn't know that they existed before. Maybe they are in the literature, but this time we actually had to construct explicitly, because before the faithful tracial state case in the AF case, the fact that we were dealing finite dimensional subspaces, C-star subalgebras, was how we got conditional expectations here. Even though we have a faithful tracial state on the entire Bunce-Deddens algebras, that wasn't a way that we could get a conditional expectation from the whole space to the subspace. We had to do it consecutively, but we were able to do it explicitly though. Anyway, that was a bit of a tangent, but we have Lip norms on the matrix algebras, okay? On the circle algebras. We have Lip norms here now, okay? Let's see how we build these, and again, that's part of the goal. And then how do we build, do we have some properties that build up Lip norms on the whole spaces, okay? Using completeness arguments, okay? However, oh yeah, so one added structure I'll mention before we move on is that another reason why we use the trace, I sort of mentioned already, but the point is that with this conditional expectation that we built explicitly, we do actually get that the trace, it preserves the trace. The conditional expectation preserves the trace at each level. So again, another nice property of why do we tack on this term to the Lipschitz constant? Right, there's other options you could do, but specifically, we use this because it preserves the conditional expectation preserves them. Okay, so we do want to actually, when we move into the Bunce-Deddens algebraic world, okay, we do have these unitaries, right? So we do actually want to get to complicate the lip norm we just had a little bit more, okay? In particular, we want to conjugate the terms we have with these matrices we'd had, these unitaries we had before, built by the roots of unity in some way. Okay. So we conjugate by that, and the reason for that is that by the construction I'm not giving, but again, there's this explicit construction of these conditional expectations. We do get that the lip norm is actually, this lip norm now is contracted with respect to the conditional expectation, which will be very important. Moving on, because again, we want to control these lip balls with respect to our estimates. We need such things like this to do that.
And excuse me, on the left-hand side of this inequality, do you want to have LMN or maybe LN?
No, in this case, because the E is a conditional expectation onto the image of alpha, which lives
Into the image. Okay.
Yeah, no, that is a good detail to point out, though. Yes, so we are using the same lip norm here. Thank you. Yeah, and this was one of our results of this paper, was that we get this. Okay. However, unfortunately, the other thing is not true, right? So the idea is we have two maps floating around. We have this embedding alpha, and we have this conditional expectation E. Okay. So the issue then is, do we get that? What about the other? Do we get contractivity with the embedding? So here we do not get the case. And the issue is that if you try to make it so, if you try to build a lip norm so that this other inequality, this non-red inequality is satisfied, you don't get the red inequality. So you do have to sort of make a choice of which one do you want to be preserved. We did the conditional expectation, but then we were able to tweak things later on in another way to get this other inequality. So again, eventually we get both inequalities, but for now we'll revisit that later. Okay, so the idea is that we want to use this theorem again. We want to have these structures floating around. Okay, so then, as I just said, we want to be able to get the contractivity with respect to the embeddings as well. So we devise a method that if you do have contractivity of the conditional expectation already, how do you build another lip norm now that has contractivity with respect to that and also estimates in some distance? Okay. So the idea then, so this is just a reminder of the goal that we want. We do want contractivity there of the embeddings, which is property 1. These are with respect to inclusion, but if you have more of a general inductive limit picture, you want to use the embeddings. So then a way to do this is the following. So do we devise the way to actually, given that we have this, and what's nice is that even though we don't have contractivity with respect to the embeddings, we do get scalars. We do get equivalence constants, okay, with respect to the embeddings. And again, here we're not using, I'm switching back and forth between embeddings and just inclusion, right? A is just contained in B. But the idea is you can always introduce the embedding later using the image of your map. So here we do get equivalence constants, right? We don't get contractivity, but because this is already satisfied, if you're careful, you can build another lip norm on the bigger space on B in the following way. So you just scale the lip norm you had on B with the inverse of K, K just a scalar, positive scalar. Okay. But then you still want to, so here we're sort of also sneaking this in. We want to be able to get close, right? So this was sort of the idea from the AF algebra picture here, which also appeared in previous works too, as well. This idea of scaling this thing. So Riefel had some estimates like this too in his work. This is a way to scale your estimate, right, to work out. And we include the composition of LA now, the lower lip norm, with the conditional expectation. Okay. And here this would be composing with the embedding if we had it in this case. Okay, so here we get contractivity. This is this line here. We do get some contractivity here. Okay, everything else is still satisfied, and we do get an estimate. Okay, with respect, because this is just, if this is less than or equal to 1, right, we're comparing lip balls, then norm of B minus B minus E of B is less than or equal to epsilon. Okay. Now, if you'll notice, this was just between two terms. The idea is that you can just recursively do this for the inductive sequence picture, right? If you have AN, A1, A2, A3, you start at A1, do this for A2, now you have a new lip norm on A2 that satisfies certain properties, then do this again for A3, and then, so you can just do this recursively. So I only showed again, just like with the building the Bunce-Deddens algebra, I just showed the consecutive picture, just to sort of simplify notation, even though it's still quite a lot. Okay, so you'll notice that in the previous slide, we only assume that ALA and AL and BLB are compact quantum metric spaces. Okay, we didn't have quasi-Leibniz in that definition. The issue is that it may be the case that this is not quasi-Leibniz. Okay, even if ALA and BLB are assumed to be quasi-Leibniz. We were able to get some estimates, but the issue is, again, when you look at the entire inductive sequence, you're getting quasi-Leibniz conditions, possibly quasi-Leibniz conditions, but they're blowing up. And the completeness argument of propinquity requires that the quasi-Leibniz condition is bounded, right? Or just, fixed, right? Well, bounded. But the issue is that we can maybe get some quasi-Leibniz conditions here at each AN, but the problem is that they blow up as n increases. So unfortunately, we cannot use, and the issue for that is that the space you get in the end may not be a C-star algebra because you're not preserving the multiplicative structure. So this is quite unfortunate. Okay, however, not all is lost because you can still study compact quantum metric spaces on their own. And you can use, for example, Riefel's Quantum-Gromov-Hausdorff-Distance to do that. Okay, this shows convergence between compact quantum metric spaces. Okay, so now we introduce, as we mentioned earlier, Riefel's Quantum-Gromov-Hausdorff-Distance. What's nice is that we can actually already use the tunnel notation before that we introduced. So Riefel's Quantum-Gromov-Hausdorff-Distance, you can think of it's sort of built using some specific tunnels. So the idea, it's built using tunnels on the direct sum, and not just tunnels on the direct sum. It's also using the surjections in this case are just the standard surjections, the ones that just take AB and map it to A and an element to AB and map it to B. Okay, to the second coordinate. And also no Leibniz condition is mentioned on the space. Okay. Because of course you're not assumed to have any Leibniz condition to begin with. Okay.
Excuse me.
Yes.
So the freedom is only in the choice of L. Yes.
Yes, essentially. Yeah. That really is. Yeah. The freedom is in choice of L.
Thank you.
Mm-hmm. Yeah. Okay. And then we define just in a similar way. So here we do just take. We don't do this thing Latremer did with the, comparing with the state space on all of A plus B. We just compare directly. So this is more of the Gromov-Hausdorff-Distance picture. We just compare directly the image, the isometric image of state space A and the isometric image of state space B. Okay, and this does give us a complete metric, but it's not up to, there's an algebraic structure here. So it's an order unit isomorphism whose dual maps are, so you still get isometries with respect to the state spaces via the dual maps, okay, of the isomorphism, of the isomorphism. Okay, so this is okay, so let's use this then, okay. However, an issue arose when we try to analyze using Riefel's quantum distance is that the completeness argument is different than Latremer's completeness argument, okay? And the thing is, we already did so much work already using Latremer's completeness argument that we thought, okay, either we try to switch it to using Riefel's completeness argument or we think of something else. So we decided to think of something else, okay? So the idea is maybe we can still use the dual propinquity, Latremer's dual propinquity, motivated by Riefel's Quantum-Gromov-Hausdorff, how that was built, meaning let's just switch out. So these surjections, for instance, are they are star homomorphisms, okay? But in particular, they're just order unit preserving maps. So we thought, okay, let's look at propinquity now, and maybe let's just define an order unit dual propinquity, okay? So that's what we did next, okay? Then maybe then we can still use Latremoyer's completeness argument, okay?
Can you remind me what this order unit means?
So an order unit space is a vector space with an order on it. So an example is just the self-adjoint elements of the C-star algebra is an order unit space. So it has a unit and an order.
What kind of order? Is it a partial order?
Oh, it's a partial order. Yeah, partial order. Yeah. Yeah.
So say again, so what would be an example?
The self-adjoint elements of a C-star algebra.
Self-adjoint elements, okay.
Yeah, self-adjoint elements. So just the and then you have the order of positive.
Yeah.
No, positive. Yeah, A is less than equal to B if B minus A is positive.
Yeah. Okay.
Yeah.
Okay.
Yeah. So all the examples in this talk are just using the self-adjoint elements of a C-star algebra. Except in the completeness argument, it just spits out an order unit space. You don't know whether it came from self-adjoint elements, some C-star algebra to begin with. Okay. So we have so we define an OU tunnel now. A lot of different tunnels in this talk. To be a tunnel such that pi A and pi B. So here we don't need A plus B. Okay. So here the freedom is that E doesn't have to be. So you have the freedom in E and also the equilibrium. It just has to be a space that there exists surjections. So also the surjections don't have to be the canonical surjections because you don't have canonical. You don't know what E is. E doesn't have to be the direct sum. Okay. So basically all we did is just replace. We took the original definition of tunnel. We don't require E to be a C-star algebra. It just has to be some order unit space. And we just require pi A and pi B to order unit surjections to be order, so they don't have to be they don't have to be multiplicative in any way, right? Okay. So and LE need not be Leibniz as well, because again, we're not even assuming that we have quasi-Leibniz or any other Leibniz condition. Okay. So we define the order unit propinquity to then be the infimum. So this is now, we're still using the extent. I should have probably, I don't think I did. I should have probably redefined the extent here. But the extent was that quantity that compared state space of A with state space of E, and then with the Hausdorff distance in the quantum metric, and separately compared the state space of B to the state space of E there, and then took the max of those. So it sort of did a separate, it looked at things individually and then took the max. Okay. So this does still give you a complete metric up to order unit isomorphism whose dual maps are isometries on the state space. Okay. So again, we don't have metric up to star isomorphism, but at least we preserve the unit and we're bijective.
So chi is the extent, right?
Yeah, chi is the extent, which is this quantity that compares state space of A with state space of E, and state space of B with state space of E, and then takes the max of those quantities. So it doesn't directly compare state space of A and state space of B. It uses an intermediate step with state space of E. Okay. So then, interestingly enough, so there are some differences here with the previous slide, right? Again, we don't require our space to be A plus B, so therefore we don't require the surjections to be anything. They just have to be order unit surjections. And interestingly enough, when we remove so we're just removing multiplicative structure. We're just taking the original propinquity construction, the dual propinquity, removing any multiplicative structure. That's all we're doing, and we're still getting structures, tunnels that are still quite different than these R tunnels, which were essentially refill bridges before. A lot of confusing terminology in this area, unfortunately. And I'm making it more confusing by calling this an R tunnel. I should have just called it a refill bridge. But then, so these are quite different tunnels, okay? But in the end, you can actually show that the dual propinquity, the order unit dual propinquity is Riefel's Quantum-Gromov-Hausdorff-Distance. So this is actually quite satisfying. So meaning we can just use Riefel's Quantum-Gromov-Hausdorff-Distance with all the advantages of, well, based on our work, the advantages of having the completeness argument of La Tremere. Okay, so this was a nice thing we got, even though the tunnels are a priori quite different structures. Okay, so the idea is that we want to recover the inductive limit. Okay, and then we still want to use this reconstruction we did before. We still want to make sure that La Tremere's completeness argument, like nothing got messy. And there is something that does get messy, and I'll get to it in a moment. So again, same idea. We take this K sub 0 space, and then we take the semi-norm. The only thing we don't do this real and imaginary part, because we have no hope to even acknowledge any C-star algebraic structure. Here we just have order unit spaces. So we don't do that. We just stop at there. And again, we are assuming our spaces are C-star algebras to begin with. We're just looking at the order unit spaces of their self-adjoint elements. So then we just take the closure with respect to the norm on D, which is just a supremum norm on the product. Okay. And then we define this subspace here, which actually gives you an order ideal in this case. So you have that if you have an element less than or equal to an element in the ideal, then you're in the ideal. However, this is where an issue arose when we took the quotient. So the quotient, you get a vector space. The quotient is defined, but what is it? So this actually took some time because the structure is quite involved. But quotients of order unit spaces aren't so nice. A quotient by take a the work of Siegel and Irving and all these great mathematicians. They show that we have that if we quotient by a C-star algebra, a C-star algebra by a C-star algebra, quotient by an ideal of the C-star algebra, a C-star algebraic ideal, you do actually get a C-star algebra as a quotient, okay, with the quotient norm. Okay, everything works out very nicely. Unfortunately, order unit spaces, you can take a quotient, you can actually get different order structures, okay, and you may not even get an order unit space. So, so this is very tricky, but eventually we do show that that's an order unit space. Seems like a very like basic thing that why I even mention it, but this was tricky. You do get an order unit space that you're able to use estimates with respect to the norm on it, and that we used before in the C-star algebra setting. So of course we don't have C-star algebra here, but we get a nice enough order unit space. Not only do you get an order unit space, but it's nice enough to give us estimates with the quotient norm in the right direction to be able to still get our results, meaning we still get not only a lip norm on F, but we're still able to build an isomorphism, an order unit isomorphism. So this is why we wanted an order unit space, right? We need to be able to build an isomorphism with another order unit space. And we want to make sure it's nice enough of an order unit space. So that's why I state this. I put our name on that result. But yeah, so then this is, again, the whole A is not considered, but at least we get the order unit space of self-adjoint elements, and then we're able to define a lip norm on there. And ALA is a compact quantum metric space. So we are able to use, we are able to do our construction here. Okay. Yeah, so then just showing that we did accomplish the task. This is just the theorem saying that we do get lip if we have contractive lip norms and we have this estimate. So here we just made it more explicit with respect, because we're not talking about bridges anymore explicitly. We do have estimates. Here are the estimates that gave you the estimates in the bridges before that we have. Here we're just using tunnels, so we didn't want to mix up further language. We assume the beta sequence we had before is a psi sequence for some reason now. We assume it's summable. And so we do get this estimate, which automatically gives us convergence, right? It's the tail of a summable series. So we get convergence, okay? And then, yeah, so for each sequence, Kn, this is the Kn divides Kn plus 1, there's this lip norms LKN on here. So these are the lip norms we built before. By that consecutive construction, we just did it recursively for all n. This is lip norms we build on those. Then you get a lip norm on the entire space, where we get convergence in Riefel's Quantum-Gromov-Hausdorff-Distance. or this order unit dual propinquity, same thing now. And furthermore, we do get that if you consider these positive integer sequences as living in the bare space, which is this the space of positive integer sequences, and you look at the bare metric, which gives you the cylinder set topology on the sequences. So a sequence of elements of the bare space are converging if their terms are agreeing on longer and longer initial segments. So if you do have that, then you also have, this is a continuous map to the Bunce-Deddens algebra. So this is nice. We don't just get convergence of the circle algebras to the limit circle algebra. We also get convergence of just the Bunce-Deddens algebra, the entire spaces themselves, if we just vary their, we're considering the parameter being just the positive integer sequence that builds them. Yeah, so we're able to. It was quite a journey from the AF case and C algebra realm, but we had to dive into the order unit realm. I mean, eventually we the next step is to get lip norms, some quasi-Leibniz lip norms on there, but for now we just sort of approached it from just the circle algebra case and see what we can do there. Anyway, thank you for your attention. Thank you for staying. Again, terribly sorry about the being late. But yeah, thank you.
Okay, thank you very much. So let us virtually clap hands. Okay, and now we can begin with questions. Please fire at will. Anybody, any questions?
I have questions.
Go ahead.
Yeah. Yes.
Okay, so the first question is, how different from Gromov-Distance Hausdorff?
Gromov-Distance Hausdorff.
Sorry, from Gromov-Hausdorff-Distance can be this propinquity for classical finite metric spaces?
I don't have the estimate. I only have the reference, and so this would be the same estimate that you have for how far the Quantum-Gromov-Hausdorff-Distance, Riefel's Quantum-Gromov-Hausdorff-Distance on classical spaces is from the Gromov-Hausdorff-Distance. So I know that it's the example that's brought up is in Riefel's paper, Gromov-Hausdorff-Distance for quantum metric spaces, and there he has an appendix from Hanfeng Li, where he does show, like, he does give an example. I forget the exact estimate off the top of my head, but there is. I mean, there's not like a global estimate, I should say. There's just a counter example, or an example where the inequality is strict. So, but as far as like, is there a more like concrete how far it can be in general? I mean, they could be equal. I guess I don't want to say that being recorded. I don't want to say they could be equal, but yeah, sorry. Yeah, sorry. I do not have a explicit answer for that. But.
Okay. The second question: what happens to the theory when one restricts it to pure states only?
So pure states, I believe you do get. I believe again, you do get better. I mean, you do get equality, but the problem is that I think you do get equality in that setting. But I would check Riefel's paper because he does mention things with the pure states too. The issue is that the pure states are in the non-commutative setting, they're not compact in general, right? The pure states, and in fact, they can be dense in the state space. I believe this is true for the irrational rotation algebras. So in that sense, we can't really use any sort of compactness arguments or we can't use. So we only get nice things in the classical setting on the pure states, but once you do the non-commutative realm, you have non-compact sets, and estimates then become quite nasty. So, yeah.
Okay, so next question: can be this theory extended to the unit-preserving CP maps instead of states?
Yes, yeah, that was actually what David Kerr had. Yeah, he does use CP maps. So David Kerr, in his, he has a paper on the Quantum-Gromov-Hausdorff-Distance back in the early 2000s, or mid 2000s.
Who is the author? Could you repeat?
Yeah, David Kerr, Kerr.
Okay, thank you.
And he actually uses this to get distance 0, gives you a star isomorphism. So he uses CP maps to do that, which is very nice. So that's one way to get distance 0. Gives you an actual star isomorphism, not just an order unit isomorphism.
Okay, so do you know maybe if one replaces the notion of pure state by C-star extremal such CP map, does the situation is better in this CP realm?
I have not. No, I have not looked at it. So what was the map you thought? C-star.
So you said that pure states are too poor for in non-commutative case. So I wonder what could happen if we replace states by unit preserving CP maps, but we restrict ourselves only to these C-star extremal CP maps.
C-star, okay, yeah. So I need to
operator valued analog of pure states. Is the situation better?
Okay. I do not know this situation, but yeah, I mean, maybe it's something. Yeah, it could. It's a good question. I need to look into C-star extremal. Okay, maps. Yeah, I haven't seen anything about that, but yeah, no, that could be a new thing to check out.
Could I find something about this in this article by David Kerr?
I'm not sure he talks about C-star extremal CP maps, but I mean, you could find about the CP map, of course, thing there. But yeah, I'm not sure if he does the extremal map. Idea.
Okay. Thank you very much.
Yeah. Thanks for your questions. Yeah.
Anybody else? Any further questions?
Maybe I would like to ask, is it known what is the structure of all compact metric spaces, classical, within the space of all compact quantum metric spaces? Is this set, for example, I don't know, nowhere dense or something like this? How big this set is?
Yeah, no, that's a good question. Yeah, I've never thought about that. I mean, it also depends on if you're looking at the Riefel's Quantum-Gromov-Hausdorff-Distance and propinquity, because you can get some estimates by continuous self-adjoint elements of continuous functions more easily in Riefel's Quantum-Gromov-Hausdorff-Distance, but still, so it seems like that question would depend on the different quantum distance you're looking into, but I still don't know what you would get. But no, that's a very good question.
Okay,
yeah,
but the topology is the same, yes? Or
yes, the topology is the same. Yeah, topology is the same, but I mean, yeah.
Okay, thank you.
Adam, can you actually state your question one more time?
Okay, so my question was about how big the space of all compact metric space is within the space of all compact quantum metric space. For example, is this set is maybe, I don't know, nowhere dense or something like this?
Of course, up to isometry.
No. Regarding only topology. So it would be the same question for the
no, what I think Professor Hayats was saying was like you're considering each compact quantum metric space with respect to isometry. Yeah. The points are compact quantum metric spaces up to.
Okay. Yes. In this sense, yes.
Yeah.
Okay, I've got your question now. All right. Anybody else? George, would you like to ask a question?
Okay. Well, I've been wondering if you look at the general, I mean, inductive limits are a special case of continuous fields of C-star algebras. If you how generally can you well, also you have the continuous field of rotation algebras and the continuous field of UHF algebras. The supernatural numbers form a Cantor set, and you get a continuous field of the UHF algebras. Okay, and I was just wondering if you how generally, when you have a continuous field, do you have is it continuous in the quantum
There has been work to this. Hanfeng Li has some work to this, but it seems to be usually very much still a case-by-case scenario. Like I don't see, I don't think there's like there has been like a theorem like, okay, here let's just use, here's when continuous fields converge. So again, I should say Hanfeng Li does have theorems to the effect of, if you have a continuous field, then you're continuous in quantum distance. But that worked for some of his examples and maybe some other examples, but it seems that right now there's not one that's like overarching that. At least we were not able to use such a theorem. But I mean, there are such theorems with conditions, but as far as, it doesn't seem to be very general, to answer your question.
Okay, well, a related question is, if you look at the embedding of rotation algebras on a fixed Hilbert space of Hauer and Roerdam, does that so that's continuous in a strong sense as subalgebras of B of H? Is that I guess that was that be an example of sort of explicit quantum-Hausdorff continuity?
That might be. I have not. So I know that. Yeah, I know that Latremiere and Riefel have shown continuity of rotation algebras, but I don't think it was with respect to that specific structure.
Well, they might not have mentioned. They might not have mentioned it because it was so concrete. It was just also everything sitting on a fixed Hilbert space. But
yeah.
The variation of these things maybe suggests a certain kind of abstract closeness.
That may be another way of looking at that. Yeah, that's a good question.
Okay,
yeah.
well, I'm wondering if it's at least true in that case. Yeah, I mean.
I'm not sure. No, that would be, that's an interesting.
Or for that matter, another way of looking at it, you could wonder how generally the quantum propinquity can be, or closeness can be realized inside a fixed Hilbert space.
No, that it usually seems to be that sometimes we do embed and into some B of H in certain cases, but it's.
I'm afraid these aren't very precise questions.
No, they are good questions. They are precise, yes. But I definitely think it's I would.
Okay, well, thank you.
Yeah. Mm-hmm.
Thank you.
Okay, thank you very much. Thank you. Anybody else? All right. So if everybody
yes,
is
may I? Sorry.
Yeah.
Continuing question of George Eliot.
Yeah.
If you have a continuous family of zeta algebras, then you can compare different fibers in the spirit of the previous question, but you can also compare families over the same base. What is happening to this propinquity if you consider a family of these propinquities parameterized by some base family, base space?
So I would just revert to the fact that, I mean, the lip norms can be wildly different. So it really, I think, just depends on what lip norms you're considering. I mean, so once you put the quantum metric structure on there, then the question becomes much more involved. So unfortunately, I don't know of any sort of general results with respect to that, even with respect to lip
my
norms.
question was rather about this. If you have some closeness of two families.
Oh, if you already have some closeness.
What can happen in the limit of this family of closeness? Can they be in the limit very far, for instance, or they have to be still close?
I'm not
So you
sure.
said that this, of course, this Lipschitz norm can vary a lot along this family. But if you have two families over the same base, and you know that fibers of these two families are close with respect to this.
I see. Okay.
Okay. What could happen in the family? Sorry, in the limit in this family. Can close family, two close families pointwise can be very distant in the limit, for instance?
Can they? I feel like they could be far, but I can't think of an example. Yeah.
Okay.
That's a good question, though. Yeah.
Do you know any papers about this?
I have not heard that specific question before. Yeah, but no, that's interesting. Having two different families, they're both close each. Yeah, I'm not sure. I mean, maybe it's just some triangle inequality. Maybe it is basic, but I'm not sure. It could be as basic as some triangle inequality estimate, but I don't want to, say it's that easy. It doesn't sound like that easy. So, yeah.
Okay. Okay. Thank you.
Mm-hmm.
All right. So let us thank Konrad again, and let me announce the next seminar. It's going to be Magnus Goffeng from Lund, from Sweden. So we moved next week from California to Sweden, and it will be about untwisting spectral triples. I just got an abstract and it looks very exciting. So I hope to see you guys there. And for the time being, we adjourn. Thank you very much, Konrad, for your talk from the sunny California. Thank you everybody for participating and making a lively discussion. And I hope to see you next time. For the time being, we adjourn. Stop recording.